Okay, great. And it looks like it is time. Jonathan Schneider is here to tell us about roto-welded knot theory. Take it away.
Okay, yes, thank you. This project is something I did with Lou and AG Ogasa a few years ago. It was my last collaboration with them. And it's been a while since I dusted off this math. I thought this would be a good opportunity to take a look at it. The basic goal of this project is to find a correspondence between a purely diagrammatic knot theory, just involving knot diagrams in the XY plane involving Reidemeister moves, with a topological model for that involving a torus in 4 space. So here on my title screen, you can see on the left the image of an example of a knot diagram, just a curve in the XY plane with crossing data at its generic transverse crossings. And our goal here is to find a correspondence to this topological model involving a torus that sits in 4 space in a particular way that gives rise to the same knot diagram. So let me start by going into some detail about these toral surfaces. Am I currently on the right screen? There we go. Yeah, so these fiberwise embedded toral surfaces, it's an idea that goes back to Colin Rourke from, I think, 2006, if I recall correctly, a way of modeling certain types of diagrammatic knot theories. The basic idea is we take a torus and place it in 4-dimensional space so that each of these blue meridional circles lands into 4 space with a constant x and y coordinate. Just each circle sits in its own little UV plane, using only the UV coordinates. If embedded just so, then all of the red longitudinal curves of the torus end up being gathered together as a red base curve in the xy base plane. And if we're really lucky, that red curve will look like a knot diagram in the XY plane. So again, each blue fiber circle, each blue meridian of the torus ends up sitting in one of these UV planes. Wherever the red curve happens to cross in the XY plane, now we're looking at 2 different blue fiber circles of the torus co-occupying a single UV plane. Sometimes 2 circles can occupy the same UV plane side by side. Sometimes one nested inside the other. And this will give rise to crossing data. That was the brilliant idea in Rourke's original paper, that we can consider just the base curve in the XY plane, essentially by just projecting down in the UV direction and allowing this knot diagram, allowing this red base curve in the XY plane to take on crossing data, formally speaking, based on how the blue fiber circles interact above the crossing. So here, a classical crossing is understood to occur wherever the fiber circles are nested, right? Each of these fiber circles comes from a different part of the torus. If one part of the torus is a thin tube and another part of the torus is a fatter tube, then one of those circles can nest inside the other, the smaller circle corresponding to the understrand and the larger circle corresponding to the overstrand. If the 2 parts of the torus simply pass by each other side by side, then the blue fiber circles will not be nested, and we can identify that formally as a virtual crossing in the XY plane. This whole situation, of course, assigning this crossing data depends on that red base curve looking like a knot diagram in the first place. It should be a generic curve with degree 2 transverse crossings and non-vanishing velocity, non-vanishing derivative of the curve, in order to get a nice generic knot diagram. So these UV projections don't really look like surfaces. They just look like a bunch of circles popping out of a curve. I'm a guy who likes to be able to visualize surfaces with full dimensionality. So here's a little device to help make that more vivid. That's the Y projection. Rather than projecting the fiber-wise embedded torus just onto the XY plane and down the UV directions, here's what it would look like if you projected it into XUV space down the Y axis. You get this Y projection, which has a nice satisfying geometry to it. You can see that the shape of the surface more or less follows the same shape of the shadow it casts on the XY plane in the UV projection. And that the crossing data, the virtual and classical crossings, are also readable in the surface, namely the virtual crossings from the picture up here. They just appear as two tubes kind of slipping past each other without interacting. Whereas a classical crossing shows a thin tube and a fat tube sort of weaving through one another. The thin tube has to jump in and then duck out of the fat tube, with the thin tube corresponding to the understrand and the fat tube corresponding to the overstrand. Notice here that I'm using a broken surface diagram where the breaks are determined by their height in the Y direction. Anything that has a lower altitude in the Y direction gets broken at one of these crossings, if you look carefully at the two images. This is really just meant to be a visual treat. I don't need the Y projection for the theory I'm developing going forward, but I hope that this picture helps convince you that we are in fact looking at a fiber-wise embedded torus in 4 space. Note, by the way, also that the extrema in the X direction, the maxima and minima in the X direction here on the far left and right, correspond in the Y projection to the tube simply flipping inside out on itself, right, with two branch points, with two Whitney branch points there and there. Think of this Y projection, if you will, as a loaf of bread, and the UV planes are how I slice the loaf of bread in order to get the UV planes and their fiber circles that you see in the picture right above it. That's really the relationship between these two projections. It's sliced up like a loaf of bread. Let's leave the Y projection behind us for now. So generic versus non-generic surfaces. Here in the upper left diagram, we have an example of a fiber-wise embedded torus whose shadow in the XY plane, whose base circle in the XY plane, looks like a knot diagram. It has all the standard features, transverse order 2 crossings only, and non-vanishing velocity as you move around the curve. So it's generic. It gives rise to a knot diagram. But there certainly are ways to put a torus into 4 space in a fiber-wise way that don't look like knot diagrams. You could have, for example, a degree 3 crossing of the base circle here, where perhaps you'd have 3 or more fiber circles all co-occupying the same UV plane. Here in the base curve on the XY plane, we have 3 strands, 3 longitudes from the torus, all crossing at a single point, and the blue meridian circles from the torus have to interact in some way in this common UV plane that they cohabitate together. Another example of something that's not generic is over here. I hope you can see my pointer in this diagram. For a certain interval, the 2 different strands of the base circle are intersecting but non-transversely, sort of coinciding for a length. Again, here I've decided to give them classical crossing data. One of these strands is considered over and the other under in their crossing data, and that's reflected in the way I drew those fiber circles in their UV plane up here. And perhaps most interesting of all is this cusp point here. The base circle decelerates to a stop at the cusp point, lingers there for a while before accelerating away in a whole new direction. You can think of an entire length of torus tube all getting crushed into this single UV plane. I tried to draw that as an annulus here. It's just a whole big slice of torus that got squashed into a single UV plane and laid out like an annulus. No reason no reason that we can't have a fiberwise embedding that behaves that way, but note that we're forced to regard this as classical crossing data, not virtual, since all of these fiber circles are automatically nested in the annulus. And perhaps a more wacky example of a non-generic embedding is the one down here at the bottom, which for the most part just looks like a generic knot diagram with virtual crossings, except at the very center where there's an accumulation of infinitely many such crossings, something that we don't usually allow in our knot diagrams, but no reason it can't happen for these fiberwise embedded tori. So I'd like to expand my theory of curves in the plane with the curves in the plane with crossing data to include these non-generic cases. Let's make that happen right now. So we're going to put aside the tori for a moment and just think about the base circle, the shadow that it casts in the XY plane. Here is a circle in the XY plane. It's certainly not necessarily generic, and we will, in a purely formal sense, define crossing data applied to this. Wherever the curve intersects itself, wherever this map K is not one-to-one, we have to designate one of those points in the domain as over and the other as under in a classical crossing, or alternatively say that they cross virtually. Okay, it's just a purely formal system for putting crossing data on a closed curve in the plane. Seems reasonable, but there are rules. We want this crossing data to lift back up to these toral surfaces that motivate us to consider this. We would like to apply crossing data in a way that is possible as the shadow of one of these toral surfaces. So there are rules about how to apply this crossing data, specifically 3 rules. Rule number 1, linearity. Whenever you have more a crossing of this curve of order 3 or more, we require that the crossing data reflect a linear ordering in the classical case, meaning here we've got 3 points of the circle all coinciding on a single point in the plane. I call them points 1, 2, and 3. 1 is the under strand, 2 is in the middle, and 3 is on the top. It's a linear order. Now we should also come up with rules that admit virtual crossings, and I've done that here. Only these 4 patterns are possible under the linearity rule. Why these particular 4? Because they can occur as shadows of a fiberwise embedded torus. Here I'm putting back the fiber circles just as a graphical convention or graphical convenience so that we can keep track of the crossing data here. So for example, look at the 3rd example on this page right here. One of these strands is over the other 2. Let's say this horizontal strand is over the other 2, and both of them are under that strand. But those 2 slanted strands cross each other virtually. That gives rise to 2 circles that are side by side, a virtual crossing, and both of them are under, meaning nested within the outer circle corresponding to the horizontal strand. So just 4 possible ways that circles can interact in the plane. I think I've accounted for all of them here. That's the linearity rule. There are more rules. In addition to linearity, we have stability. The crossing data on a curve has to follow this rule that wherever you have 2 pieces of the circle crossing each other, let's call them 2 intervals from the circle crossing each other, those 2 intervals from the circle have to cross each other where one is strictly over the other and one is strictly under the other. Without any mixing. Basically, every pair of points in the circle have to have neighborhoods such that one is entirely over or entirely under the other, or alternatively, only a virtual crossing. So here, this upper This upper example obeys stability, even at the center there where you have infinitely many virtual crossings, because even though there are two strands of the circle, two intervals from the circle crossing infinitely often there in the middle, all of the crossings are virtual, and that obeys the rule. Contrast that with the forbidden example down below, where you have a combination of over and under mixing together there. That's not going to be allowed. This picture with where I've restored the fiber circles should explain why these rules are in place, because well, what would happen in that forbidden case? The strand that I'm calling A is the over strand as we approach from the left, but then it's the under strand as I depart towards the right, meaning that it has to abruptly switch from being the outer of the nested circles to the inner nested circle, which is not possible for a continuous embedding of the torus, so we just rule it out. Okay, so rule one was linearity, rule two was stability. There is, in fact, a third rule, monotonicity. Monotonicity concerns how a single strand of that circle is allowed to cross itself. The rule is that a single strand of the circle should be crossing itself either only virtually and finitely often, or only classically and in a monotonic sense of strictly descending in one direction. So here in the good example, the permitted example, pay attention to that cusp point there in the corner. As I approach that cusp point, we're always descending. You see what I mean by that? That I've applied lots and lots of classical crossing data, but I'm always going down the staircase, never climbing back up. That's a good thing, because now when I try to lift this back up to being the shadow of a fiberwise embedded torus, it will be compatible with the fiber circles in those UV planes. Whereas in these forbidden examples, it's not going to work, because now sometimes I'm descending and sometimes I'm ascending, infinitely switching back and forth as I approach the cusp point. And what's even worse is this other forbidden example where I have infinitely many virtual crossings all accumulating together at that point. Remember that in the previous slide, I had an example where infinitely many virtual crossings accumulate at the center, but that was okay because it came from two different parts of the circle interacting. Now it's no good anymore because it's just one part of the circle interacting with itself virtually infinitely often. These three rules are enough to guarantee that the crossing data you've applied to your diagram, to your curve in the plane, is potentially the shadow of a fiberwise embedded torus. So that is pretty much all we need to establish these objects, fiberwise embedded tori and their shadows, the UV projections. It's time to talk about what happens when the torus starts moving through four-dimensional space. So again, I've set up a fiberwise embedding here. The torus goes into four-dimensional space, X, Y, UV space. Only now I'm indexing these maps over an interval of time from 0 seconds to 1 second in time. This is now 1 second long homotopy, or really an isotopy of the torus moving through four space. And the rule is that at each moment of time, it still needs to be a fiberwise embedding. So if you hit pause on the VCR, the freeze frame is going to show you a fiberwise embedding of the torus. Here, I'm starting with a generic fiberwise embedding. It's generic because the diagram in the XY plane looks like a knot diagram, nice and generic, no cusp points, no high order or non-transverse crossings. But then I allow it to start moving over 1 second of time and ending up in a different generic state, getting from the start to the ending configuration via Reidemeister moves. And you can see here a Reidemeister 3 move occurring in this example. This is what we call generic motion because it uses Reidemeister moves. What Reidemeister moves are allowed? Not every possible combination of crossing data gives you a Reidemeister move that can occur in this way. if you gather together all the Reidemeister moves that actually can occur from this type of motion, you get a type of diagrammatic knot theory that we call roto-welded or rot-welded, I believe was the term we used a few years ago. We used to call this rot-welded knot theory. I'm going to call it roto-welded today if it doesn't bother anybody. These are the 7 moves that can occur. Classical 1, classical 2, virtual 2, classical 3, virtual 3, mixed 3, and this welded 3 move. These should all be familiar combinations of crossing data on the Reidemeister 1, 2, and 3 moves. We have just 4 different forbidden moves here. The virtual 1 is forbidden. That's what distinguishes this from the more familiar welded knot theory. Welded knot theory, of course, is a diagrammatic theory that I believe goes back quite a ways, I think to the 90s, that did allow the virtual 1 move, and otherwise it was the same as what I'm describing to you now. However, we have had to forbid the virtual 1 move for reasons I'm now going to reveal to you. Here is the rationale for why some moves are permitted and some moves are forbidden. Here, for example, I'm not going to do all 11 moves for you, but I'll just give you a few examples. Here's a permitted 3 move. It's called the welded 3 move. We start out with an overstrand and two understrands that cross each other virtually. Here you can see the fiber circles of that torus giving rise to this shadow. And as we go through the Reidemeister 3 move, sure enough, the circles are compatible. This horizontal strand right here is over the 2 slanted strands, so its fiber circle needs to contain the other 2 circles nested within it. But those 2 slanted strands interact virtually at the triple point, and so they should be side by side. And sure enough, we got 2 side-by-side circles inside an outer circle corresponding to that horizontal strand. Everything works out hunky-dory, it's all very compatible, and so this move is permitted. Contrast that with the forbidden so-called underwelded move. That's what this is called, an underwelded move. It's the same as the welded move, but I've just switched the 2 classical crossings, and look at what goes wrong now. Now, here at this middle stage, the horizontal strand has to be under the 2 slanted strands, and therefore its fiber circle needs to be nested inside both of the other 2 fiber circles, which meanwhile have to be side by side. Well, can you do that? Can you draw 2 circles side by side and a third circle nested in both of them? I would dare say not, sir. I don't think that you can draw that. So we forbid this move. This logic came from Rourke's paper, his paper from, I think it was 2006. He included all of this. He went through every single move and he showed this logic works for all the permitted and forbidden moves, with the single exception of the Reidemeister 1 move for with a virtual crossing. This was omitted from that paper at the time, which an oversight that was later corrected. Here's the reason why we only have one of the Reidemeister 1 moves. Consider the classical case. In the classical case, you've got a couple of nested fiber circles over that classical crossing, and as that teardrop squeezes shut to a cusp, those 2 fiber circles converge. They meld together into a single circle, which continues existing as the cusp point smooths itself out. Everything works out nice and continuous and smooth, and everybody's happy. Now try it with a virtual crossing and see what goes wrong. With a virtual crossing, you should have 2 fiber circles side by side over that crossing, and when that teardrop shrinks down to a cusp point, well, we should still have 2 circles side by side, but we also kind of shouldn't, because there's only one point there. There's only one point of the circle there. It's not a multi-point. So we actually should only have 1 circle there. How can you get 2 side-by-side circles combined together continuously to make a single circle? Again, I posit it cannot be done, so we forbid the virtual 1 move. Basically, the idea here is you go through every single Reidemeister move, all the forbidden moves, all the permitted moves, and see that this logic works out in every case. That's the rationale for developing roto-welded knot theory. Here's an example of how we can use the knot theory just as a diagrammatic theory to untie a complicated looking knot diagram. Here at the beginning, we start with this crazy 1, 2, 3, what is this, 5 crossing knot, 1, 2, 3, 4, 5 crossing knot. I go through several steps trying to get the darn thing untied, and I eventually succeed. Note, however, that the fact that the virtual 1 move was forbidden makes this process pretty lengthy. Otherwise, I could have saved myself 2 steps. This turning point here on the right side of the screen, that could, in principle, be untied with just 2 more moves, with just a couple more steps, using the virtual 1 move. But since that move is forbidden, I have to go the long way. Nonetheless, it can be done. So just an example of using the diagrammatic theory. So we built this diagrammatic theory specifically to reflect the behavior of these generic motions of fiberwise embedded tori, what we call generic fiberwise isotopy of these toral surfaces. That gives us this correspondence. 2 generic fiberwise embedded toral surfaces. If they are generically fiberwise isotopic, then their UV projections, their shadows in the XY plane, as knot diagrams, are roto-welded equivalent through Reidemeister moves. That pretty much follows from the definition. I'll show you the proof, but I hope you'll take a moment to understand what this theorem is saying. It's saying that as long as the torus is moving through force space in a way that the shadow it casts looks like a knot diagram moving via Reidemeister moves, then this corresponds perfectly to the diagrammatic theory of this diagrammatic knot theory that we just invented, the so-called roto-welded theory. 2 steps in the proof. Step 1, if you start out already knowing that the 2 knot diagrams are roto-welded equivalent, then you can build a torus in force space that casts those shadows and moves in a way that casts a shadow corresponding to the very Reidemeister moves that you used in the equivalence, right? That's how we defined it. Every roto-welded Reidemeister move is compatible with the fiber circles in a generic fiberwise isotopy. Emphasis on the word generic here. The torus has to move in a way so that the shadow it casts looks like it's moving via Reidemeister moves. That's what we mean whenever I use the red font for generic. It means that the shadows are moving through Reidemeister moves. So this implication should be clear. Here's the reverse implication. The converse, if you start out with a torus in force space that is moving in a way that casts a shadow that looks like it's moving through Reidemeister moves, well, guess what? That's a roto-welded equivalence. Because as I showed you before, the only possible Reidemeister moves that can be cast in these shadows are exactly the ones that we permitted in this diagrammatic theory. That was the definition of the diagrammatic theory. So the proof of this implication is just to go through each move and check the compatibility of the fiber circles. That was easy. That theorem is almost trivial. It follows from the definition. What we really want to do, what would be a lot more satisfying, is to free up these motions of the torus through force space so that it doesn't have to cast shadows that are restricted to Reidemeister moves. I would like to be able to move that torus around in force space however I want. That is to say, however I want, so that it stays a fiber-wise embedding the whole time during the process. But maybe during the process, it doesn't necessarily have to look generic. Let's look at some examples of non-generic motion of a torus in force space, of a fiber-wise embedded torus space. Before I show you those examples, though, let's just set up the proof. Set up the proof of this goal here. Let's suppose, first of all, that I've got two knot diagrams, and I know that they're roto-welded equivalent because I know all the Reidemeister moves from one to the other. Well, the previous theorem told me that I can build a torus over those knot diagrams that casts a shadow, that casts a shadow corresponding to that equivalence through those Reidemeister moves. The isotopy, the fiberwise isotopy, will look just like the Reidemeister moves using the equivalent. So that comes from the previous theorem. One of these implications is free of charge. But the opposite implication is a lot more complicated. The converse here is not so clear. This time, let's start out knowing that these two tori sitting in forest space are related by a fiberwise isotopy, but not necessarily a generic one whose shadow in the XY plane maybe doesn't look like it's just going through Reidemeister moves. Can we then nonetheless conclude that the starting and ending state were roto-welded equivalent, even though I didn't actually see the Reidemeister moves of that equivalence? Let's see. It's not so obvious. Here's the kind of thing we're dealing with here. I'm going to just show you a few examples of non-generic motion, just to give you a sense of these non-Reidemeister ways that a torus can float around in forest space while still being fiberwise embedded. I'll start out with this nice generic torus in forest space. It casts a shadow, which is a nice classical unknot diagram. But rather than move through Reidemeister moves, I'm going to shrink down all that crossing to a cusp point and then expand it out to create an entirely different unknot diagram. This does not look generic to me. And yet I still somehow believe that the state I started with and the state I ended with are equivalent in the roto-welded diagrammatic theory. I do believe that this can be done using the roto-welded Reidemeister moves. I just don't actually see it in this slide because I'm doing it in such a non-generic way. So this is an example of motion without Reidemeister moves. Here's an even crazier example of non-generic motion. In this case, I'm going to start and end with just a trivial unknot diagram, just a basic loop, because the way it's about to move, the way this torus is about to move, is pretty nuts. It does some kind of classical Reidemeister 2 move on itself, and then undoes that Reidemeister 2 move, but then does it again and again, going back and forth like a vibrating guitar string, each time with a slightly lower amplitude, until eventually it converges into this non-generic diagram at time 1/2, and then opens up again. Basically, I've performed the classical 2 move infinitely often, over and over, but smaller and smaller and smaller each time until I get a non-transverse crossing at the end, and then I just open it up. This is perfectly legitimate motion for a fiberwise embedded torus in forest space, and yet it doesn't look like a transformation of knot diagrams according to any diagrammatic theory I know. Basically, what our goal is here is to start from a non-generic transformation, a non-generic isotopy of this torus, and replace it with one that happens entirely using Reidemeister moves. So here, again, is that example of just an unknot diagram that shrinks all its crossings down to a cusp and then opens them up into a completely different unknot diagram. Let's replace that with the same process, only via Reidemeister moves. What we need to do to finish this theorem is show that this replacement is always possible. That's our main goal here. Now, in order to approach this goal, it would be nice to learn a bit about what these non-generic motions can possibly look like. So it might not surprise you to learn that there are, once again, rules. 3 rules about what these non-generic motions or possibly non-generic motions might look like in terms of their crossing data. It turns out to be almost the exact same as the three rules we had for static objects. Motions in static objects also obey linearity, stability, and monotonicity. Let me show you how it turns out this time. So for linearity, again, during an isotopy, during a fiberwise isotopy, we just insist, of course, that any high order crossing of the base curve has to have its fiber circles interacting in a compatible way, right? So that's easy. The fiber circles have to interact in a compatible way. It's the exact same four patterns I showed you earlier in this talk. That's rule number one. Rule number two, stability. You can't abruptly change crossing data just out of nowhere during an isotopy. Here, I am imagining a torus whose longitudinal curve in the XY plane kind of looks like this infinity symbol, this kind of figure eight curve, this infinity, starting out with a classical crossing in the middle, and then for some reason, at time t equals 0.5 seconds, abruptly changing into a virtual crossing out of nowhere. This is absolutely verboten. It is not compatible with a nice, well-behaved embedding of the torus into four space, so we forbid it. The rule is that in this cylinder representing the isotopy, right, with the time axis being vertical here, any 2 points of that cylinder have to interact with each other with the 2 points have disk neighborhoods where one disk neighborhood crosses the other, either only over, only under, or only virtually. Seems like a pretty reasonable rule to apply here. There is a third rule, monotonicity, about what these fiberwise isotopies are allowed to look like, or I guess what I should say, how they can look. And this time, I'm not even going to bother starting from the beginning here. Let's just start with a weird non-generic shape here and see that this is a permitted move because any point of the cylinder crosses itself either only classically or only virtually, and every slice is monotonic in that the classical crossings should be strictly descending or strictly ascending, not some wacky combination of them. So this is an okay example here. You see, I've taken all these infinitely many little kinks and I've shrunk them all to a cusp and then smoothed it out. Turns out, yes, indeed, a torus can cast this shadow as it moves through four-dimensional space. So the existence of these non-generic moves is a bit of a thorn in my side if I want to complete the proof of my goal theorem. Setting these rules is just a starting point to trying to show that we can get rid of these non-generic types of motions and replace them with well-behaved Reidemeister moves. Our goal, again, is just to show that any kind of fiber-wise isotopy of a torus in four space, no matter how ugly and non-generic it is, can simply be replaced with one that's pretty. If we can show that this replacement is always possible, then we've completed our correspondence of roto-welded diagrammatic knot theory with these fiber-wise embedded tori as a topological model for the knot theory. Now, this work is work I did with Eiji Ogasa and Lou Kaufman, and I kind of left it off a few years ago, and realizing now that I've never really fully convinced myself that we have this replacement in the bag, that we've quite established this. So my goal is to just kind of tidy up this theorem over the next few months. I was grateful for the opportunity to present it today. So thank you very much.
Where are we? Greek islands? Where's that picture taken?
What did you say,
Jonathan? Is
Lou?
that where is that picture taken? Is that in the Greek island?
Oh, yes, excuse me. This is yes, at Greek islands. This was my hairstyle when defending my PhD dissertation. This was Lou Kaufman's hairstyle.